So you've got like a really interesting story you were just telling me about, a career path from hardware to sort of algorithms and software. Why don't you run us through that a little bit?
Sure. So my background is computer architecture, right? And defining, first for 10 years, I was defining CPUs, designing and defining for Infineon and MIPS. And then later in 2011, I joined in Nvidia on the mobile chips, the Tegra. And from there, I moved more and more towards computer vision acceleration, AI acceleration. From Nvidia, went to Apple. We invented the neural engine at Apple. It's a scalable inference engine, which is in every Apple product.
Wow.
And then from there to data center in Intel, large clusters, and then Google TPU.
Right.
As an architect, I always have to look end to end and the overall problem. So it's not only the hardware, I had to deliver the hardware, but there's also the software part. So it's important to understand the algorithm in order to define the accelerator. And so since I talked a lot with hardware takes 3 to 4 years to develop, so I had to look into the future. And so I usually worked with the smartest people on the algorithm side to understand where the future is so that we can define the hardware. But this inspired me actually to dive deeper into the algorithms and actually switch sides. And so this is why I joined INFRA, the AI company. Towards Superintelligence, we pre-train models from scratch with a custom model architecture beyond the transformer, with custom data, and also create enterprise agents.
Wow, that's a pretty rich set of topics there. So let's maybe start with some of the more interesting questions that come to mind. There have been a lot of shifts, obviously, hardware and software shifts, but if you were to summarize, what have been like the biggest shifts from when you started working on these systems to, the level of parallelism we're seeing right now in the hardware and how that obviously impacts the algorithms?
Right. Originally, I remember when I did some internship in the 90s actually on self-driving cars, and I talked about why don't we use neural nets and AI for that. Actually, 90s was anyway too early for the whole problem. Yes. So everything was one CPU, very slow, and you can add maybe 4 of them.
There was no parallelism back then.
You can maybe add 4 CPUs, but it doesn't have that much, right? And nowadays, of course, things are very different. And Nvidia, for example, invested early in parallelism, but also other companies as well. Yeah. This, of course, helped a lot. This is a breakthrough with AlexNet in 2012.
Exactly, yeah.
Where we had several things together. We had the GPUs. We had the data sets, the large data sets, annotated images, ImageNet, and the algorithms. So we had everything together so that the breakthrough could actually happen and people saw the value of computer vision in 2012. And then later on, similar things happened with large language models. Yeah. The data sets became bigger, large web crawls. The transformer architecture was there. Somebody scaled it up, and then suddenly we had large language models. Yeah. And so this was another breakthrough. And without parallelism, this would have not happened that easily. Yes.
Exactly. I think people underappreciate the complexity and sophistication of algorithms in this massively parallel world. You mentioned, obviously, you're working on superintelligence and agents. So what have been some of the interesting lessons learned you can talk about, in this world, particularly, from the simplistic GPT-2, GPT-3 type of, attention world, transformer world?
Right. So it's amazing how well actually LLMs work, how well with scaling they actually improve. And then, of course, with better model improvements in the model architecture, improvements in the training methods, improvements in the data quality for pre-training the models, it's also very important. Yeah. Before, people just used huge web crawls, random data pretty much from the web. And now they started, of course, organizing it, see what's relevant, what is actually not so good to use.
Exactly.
Some horror movies maybe not useful for more exactly horror books you might not want to use. And then, of course, replication, deduplicate data. So having a good data pipeline is key. And doing it in an efficient way, because you can spend an army of people on sorting data. And then, of course, it's also the algorithm side perspective. Yeah. So things have changed. And then, of course, the next level was integrating this into applications, creating agents, and then a swarm of agents. So that's the next level. So a lot of things are happening.
I'm glad you brought up that term, because one of my favorite expressions is there's no such thing as an agent in this world. It's either a swarm or no agent at all, right? There's so many parallel subtasks that get created by agents.
Right.
So that leads me to one of my favorite topics, which is, Agents, of course, put like real stress on KV cache and that kind of memory.
That's right, yes.
What are some of the lessons you've learned in terms of basically working continuously in like a KV cache saturation situation?
Exactly. So I think it's super important to, of course, optimize the systems constantly, right? And in the industries, the whole world is kind of optimizes. Not only about the hardware, not only about the compute chip or the system. You have to also optimize the way you run the runtime, this KV cache handling to make sure it's efficiently done. You can disaggregate the inference with prefill and computes on prefill and decode on different nodes. You could compress KV cache. There are many ways on KV cache optimizations. One thing at INFRA, we are looking into a better way of attention, which is less than a quadratic behavior. So there are various things to optimize the whole. Without optimizations, it's very costly. Just waiting for the next hardware alone is not sufficient. We have to look at every aspect in order to get the tokens per dollar down. Otherwise, it's to make
and optimizations are not obvious, right? Some of them work, some of them don't. Some of them have too much of a quality or latency.
Right. It always requires experimentation. Without experimentation, it's hard to make it work.
So where do you sit in? Okay, we're almost wrapped up here and getting time. Where do you sit on sort of the camp of reinforcement learning, right? Is it do you think like the vital next step towards ASI in your case, or is it just another sort of incremental scaling law that we're really finding useful right now?
Absolutely, super important. Reinforcement learning is a very critical to get to the next level. Of course, we beyond pre-training and mid-training, post-training, right, and inference with reasoning and is critical. And then of course reinforcement learning is very important to get to a high quality results.